Transformers are game changers in the field of electrical energy transmission and distribution. The invention of power transformers towards the end of the 19th century made possible the development of the modern constant voltage AC supply systems, with power stations located many miles away from our homes. This incredible machine operates at hundreds of thousands of volts and can handle millions of watts of electrical load. In this video, we are going to explore the working of this incredible piece of engineering. So without further ado, let's start it. A transformer is used for increasing or decreasing the voltage levels of an AC supply, with a corresponding increase or decrease in current. It is a static machine, which means, unlike an electric motor, which has a stationary part called the stator and a moving part known as the rotor, a transformer does not have any moving parts, except for the OLTC and motor drive unit, which we will discuss later in this video. Due to having no moving parts, transformers do not incur any frictional or windage losses, making them one of the most efficient electrical machines. Before diving into the working of a power transformer, let's first take a look at the fundamentals of a transformer. When we move a magnet near a coil, a voltage is induced in the coil. This occurs due to a change in the number of magnetic field lines passing through the coil, or alternatively, we can say there is a change in magnetic flux linking with the coil. This phenomenon is known as electromagnetic induction. The strength of induced voltage depends upon the number of turns in the coil, the strength of the magnetic field, and how fast we are moving the magnet, or we can say, the rate of change of flux linking with the coil. A change in magnetic flux is absolutely necessary for electromagnetic induction. If we stop moving the magnet, no matter how strong the magnetic field of the magnet is or how many turns are there in the coil, no voltage is induced in the coil. Let's replace this bar magnet with another coil. If we connect this coil to a DC supply, the magnetic field produced by the coil looks very similar to the magnetic field of the bar magnet. As the magnetic flux linking with the first coil is not changing with time, no voltage is induced in the first coil. That's why electromagnetic induction does not work with a DC supply. Now, instead of a DC supply, if we feed an AC supply to this coil, an alternating magnetic field is formed. This varying magnetic field creates a change in the magnetic flux of the first coil, and hence, a voltage is induced in the first coil. This is called mutual induction, and it is the working principle of a transformer. Similar to this setup, a transformer consists of two coils, wrapped around a ferromagnetic core. These coils are made with copper, coated with a thin layer of varnish or insulation. The thickness of this coating depends upon the desired level of insulation required. Varnish coating serves to insulate each turn of the coil, preventing any bypasses and ensuring uninterrupted current flow along the entire length of the coil. When either of the two coils is fed with an AC supply, the alternating magnetic field produced by that coil links with the other coil, inducing a voltage. However, this transfer of electrical energy is very inefficient because only a small part of the magnetic field from the first coil links with the other coil. To improve efficiency, coils are wound around a core made of ferromagnetic materials like iron or steel. The coil connected to the supply is called the primary winding of the transformer, and the coil on the output side, or connected to load, is called the secondary winding. The flux produced by the primary winding, which links with the secondary winding, is called linkage flux, while the flux produced by the primary winding, but not linking with the secondary winding, is called leakage flux. It's important to note that leakage flux does not contribute to the transfer of electrical energy, and therefore should be minimized to improve the efficiency of a transformer. A transformer core acts as a pathway for magnetic flux, providing a low reluctance path. As a result, most of the magnetic flux produced by the primary coil links with secondary coil. making the transfer of electrical energy more efficient. As the core is also made up of conducting material, the alternating flux passing through the core induces loops of current inside the core due to electromagnetic induction. These loops of electric current are called eddy currents. Eddy currents cause energy loss inside the core in the form of heat, which reduces the efficiency of a transformer. That's why, in a transformer, a laminated core is used instead of a solid ferromagnetic core. A laminated core is made up of thin sheets of iron or steel, each coated with insulation. These sheets are tightly held together to minimize the air gap between them. The insulation on the sheets blocks the flow of eddy currents by providing high resistance, thus minimizing their formation. And that's how a laminated core minimizes eddy currents and makes the transfer of energy more efficient. As we know, an electric motor is used to convert electrical energy into mechanical energy. However, a transformer is different. It does not convert electrical energy into any other form. Instead, it transfers electrical energy from one voltage level to another. The input and output voltage of a transformer are related according to its transformation ratio. Here, NP and NS are number of turns in the primary and secondary winding, respectively. If the number of turns in the secondary winding are higher than on the primary winding, the voltage induced in the secondary winding is higher compared to the primary input voltage, while the current in the secondary winding is lower because energy is conserved. This type of transformer is called a step-up transformer, and it is used for increasing the voltage level of an AC supply. On the other hand, if the primary winding has more turns compared to the secondary winding, the voltage induced in the secondary winding is lower than the primary input voltage, and the secondary current is higher. This type of transformer is called a step-down transformer, and it is used for decreasing the voltage level of an AC supply. An important point to note is that a transformer does not affect the frequency of the AC supply. The input and output of the transformer have different voltages, but the same frequency. Now, let's understand what are transformer tappings. A tapping in a transformer is a connection point along the winding that allow access to a specific portion of the coil. Tappings are used to adjust the voltage ratio between the primary and secondary windings, enabling the transformer to provide different output voltages. Based on how the primary and secondary windings are placed around the laminated core, transformers are generally of two types: core-type transformers and shell-type transformers. As we have already discussed core-type transformers, let's now focus on shell-type transformers. The working principle of a shell-type transformer is the same as that of a core-type transformer. The only difference is in their structure. A shell-type transformer also has primary and secondary windings placed concentrically on a laminated ferromagnetic core. In this design, the core surrounds a significant portion of the windings. Both core and shell-type transformers can produce similar characteristics. The choice between core and shell-type construction is typically determined by factors such as cost, insulation stress, heat distribution, and weight. Both of these are single-phase transformers, meaning they operate on a single-phase AC supply. Single-phase distribution transformers are also an integral part of power system. These are step-down transformers that reduce the high-voltage AC input from the nearest substation to 120 or 240 volts, which is the voltage used in your home. High-voltage single-phase AC input is fed through HV bushings. We will discuss high-voltage bushings in detail later in this video. It is a pole-mounted single-phase distribution transformer, meaning it is installed on electrical poles and has a power rating of a few hundred kVA or less. In contrast, three-phase transformers are used for high-power applications. A three-phase transformer operates on a three-phase AC supply, which consists of three individual phases with a phase difference of 120 degrees between each phase. The power ratings of three-phase transformers can reach hundreds of MVA, depending on the specific transformer and its design. High-power rating transformers typically work on a three-phase supply instead of a single-phase supply, because three-phase systems are more efficient for transmitting and distributing large amount of power compared to a single phase. Now that we've covered the basics of transformers, let's dive into the specifics of how a power transformer operates. Let's start with the heart of a transformer, the core. In any efficient power transformer, the core isn't just important, it's absolutely essential to its operation. Without it, nothing else would work as it should. A power transformer core is built from thousands of thin laminated sheets made of ferromagnetic materials like silicon steel. The purpose of transformer core is to provide a low-reluctance path for the magnetic flux that links primary and secondary windings. The alternating flux, which links primary and secondary windings, causes vibration in the laminated sheets, generating loud, unwanted noise and leading to energy loss. To minimize these issues, the laminated sheets are tightly secured together. Let's now focus on how the windings are placed on a power transformer's core. First, an insulation sheet and an insulation cylinder are placed to insulate the windings from the core and protect them from damage caused by the core's sharp edges. This cylinder is made from electrical insulation materials. 3 pairs of low voltage and high voltage windings are placed concentrically on each limb of the core. In a 3-phase transformer, each pair of low voltage and high voltage winding corresponds to one phase. The low voltage winding is always placed near the core because it has a low voltage rating, making it easier to insulate from the core. The winding arrangement of power transformer also includes axial and radial spacers. Axial and radial spacers, typically made from insulating materials like pressboard, epoxy resin, or other high-strength insulating composites. They prevent winding deformation under mechanical stress, ensuring long-term reliability and performance. These spacers provide proper gaps or ducts between different conductors, allowing transformer oil to flow and cool the windings. Additionally, axial and radial spacers ensure proper insulation and structural integrity. Transformer windings are made of high-conductivity copper due to its excellent mechanical properties and high electrical conductivity, making it an ideal material for this application. For all transformers with ratings larger than a few kVA, rectangular section conductors are used instead of the normal round conductors. This is because windings with rectangular section conductors have a good space factor and high mechanical stability. Copper conductors are covered with paper insulation. High-power transformers use paper insulation instead of varnish or enamel coating because paper insulation can better withstand higher temperatures without degrading, provides greater mechanical and dielectric strength, allowing it to endure high voltages without breakdown. In a 3-phase transformer, each phase consists of a pair of low voltage and high voltage windings. In a low voltage winding, the number of turns are much less compared to a high voltage winding. As the name suggests, the voltage level in the LV winding is lower than in the HV winding, and the current is very high according to the transformation ratio. The exact voltage and current ratings of the LV and HV winding depends upon the specific transformer. Helical winding is mostly used for low-voltage windings in power transformers. It's the simplest type of winding and is ideal for low-voltage, high-current applications. In a helical winding, the conductor is shaped in the form of a helix. The amount of current in the LV winding of a power transformer can be thousands of amperes, which is why a very thick conductor is used for the LV winding. However, using a single solid conductor can cause eddy current losses. To mitigate this, a continuously transposed conductor is used in a low-voltage winding instead of a single solid conductor. A CTC consists of multiple strands, each insulated from the others by varnish coating. In a CTC, the position of each strand continuously changes along the length of the cable. This prevents circulating currents caused by differences in the induced voltage of each strand. High-voltage windings have a greater number of turns compared to low-voltage windings, although the conductor cross-sectional area is significantly smaller. HV windings are typically wound using continuous disc windings. In a continuous disc winding, conductors are wound in continuous spirals, alternating from inside to outside and outside to inside, forming disc-like structures. These discs are connected through inner and outer crossovers. The continuous disc design ensures more uniform voltage distribution across the winding, reducing the risk of insulation failure. Power transformer windings are connected in either star or delta configuration, depending on the design of the transformer. We will discuss about star and delta connections in a future video. In a power transformer, and support structure made of insulating materials like pressboard is used for providing mechanical support and electrical insulation. Crepe paper tubes and SRBP tubes are employed for ensuring secure and effective connections. Almost all power transformers require adjustment of their voltage ratio to operate effectively under variable load conditions. This is achieved by adjusting their transformation ratio using tappings. Tappings are placed on the high-voltage winding because high-voltage winding is more accessible, as it is positioned outside of the low-voltage winding. Additionally, the lower current in the HV winding simplifies the process of switching between different tappings. An on-load tap changer is used to switch between taps to maintain the output voltage of a transformer during variable load conditions. It consists of two main parts, a diverter switch and a tap selector. The operation of an on-load tap changer is mechanically operated by a motor drive unit through a bevel gear mechanism. All of these components, including the core, windings, tappings, and on-load tap changer, are enclosed within a sealed chamber known as the transformer tank. The terminals of the low-voltage and high-voltage windings are brought out of the transformer tank through bushings. Transformer bushings are essential components designed to withstand high electrical and mechanical stresses. In a transformer, we have both low-voltage bushings and high-voltage bushings. The bushings connected to the low-voltage windings are called low-voltage bushings, while those connected to the high-voltage windings are called high-voltage bushings. For low-voltage windings, simple porcelain bushings are used. A porcelain bushing mainly consists of a central conductor, surrounded by a weather-resistant, insulating structure made from high dielectric strength ceramic materials like porcelain. For the high-voltage side, oil-impregnated or resin-impregnated condenser bushings are used, as they are designed to withstand higher voltages. A condenser bushings consists of a central conductor, surrounded by a condenser and a porcelain insulator. The condenser is made up of layers of metal foil and insulation paper impregnated with oil or resin. This arrangement acts like numerous capacitors connected in series. This configuration ensures a uniform distribution of voltage within the bushing. These types of bushings are filled with insulating mineral oil to further enhance their voltage handling capacity. The top of the bushing includes an oil expansion chamber to accommodate the expansion and contraction of the oil due to temperature changes. Insulating oil is crucial to the operation of a power transformer. The main tank of a power transformer is completely filled with insulating mineral oil, known as transformer oil. This oil is stable at high temperatures and possesses excellent electrical insulating properties, providing both cooling and insulation to the transformer windings. An additional smaller tank, known as the conservator, is used to store excess transformer oil. The conservator is connected to the transformer tank and ensures that it is always completely filled with oil, preventing any oil shortage inside the transformer tank. Transformer oil is extremely important for the insulation of a power transformer, and a shortage of oil in the transformer tank can even lead to transformer failure. A power transformer is a large and complex machine, and there are still many concepts and devices related to it that I haven't covered in this video. If you enjoy this type of content and found this video helpful, please subscribe to my channel and give it a like.